In this lesson, we're going to solve optimization or max-min problems by applying mathematical models and their derivatives to determine, interpret, and communicate the mathematical results. So as a recap, let's talk about what's happening to a function at its maximum or minimum point. So when we have a max or a min, we know that the derivative is 0. And why is the derivative of a function 0 at a max or a min? Because the slope of the tangent would be 0 at that point, and this just means that the function is changing direction. So how can we determine the max or min of a function solely based on its equation? We kind of did this in the last lesson. So first thing we did is find the derivative, f prime of x, and then we want to set it to 0, and then solve for x, and then we want to check our critical points and our endpoints. This is extremely useful because if we have a function that is essentially a mathematical model or representation of a real-world scenario, we can easily find the location of a max or min value. As our first example, a farmer has 600 meters of fence and wants to enclose a rectangular field beside a river. Determine the dimensions of the fenced-in fields in which the maximum area is enclosed. Fencing is not required to the riverside. First thing I want to do is draw a diagram, and we know that our perimeter is 600 meters. Now let's label our diagram. We can call this the width, and this is going to be the length. So essentially we know the perimeter is equal to 2 times the width plus length. And we know that the perimeter is 600, so we can set that equal to 600, and we just get 2w plus L. And we want to maximize the area. So the area of this would be length times width. Okay, so now we have two equations, and really two variables, well, three variables here, but two variables in essence. So let's actually solve for one of our variables. So L is an easy one to solve for. L we can say is 600 minus 2w, and if we want to solve for one of our variables, so in this case it would be w, we would substitute L into here, just like we did with systems of equations, and then we can just say A with respect to w is going to be equal to 600 minus 2w, which is essentially L, times w. And expanding this, we're just going to get 600w minus 2w squared. So now the question is asking us to maximize the area. So we want to maximize the area, which means maybe we should take the derivative and set it to 0. So we're going to take the derivative, which is 600 minus 4w. Let's set that to 0. And we're going to get, just going to skip a few steps, w is equal to 150. So we know that this is going to be the maximum area, the width at the maximum area. And once we have that, we can figure out what our maximum area is by substituting 150 to figure out what our actual area is going to be, and it's going to be 45,000. And now we can also find our length, so just substitute 150 into width and we get 300 meters. And this is going to be meters squared. Okay, so now if we think back to when we were solving our max-min problems, we were always checking our endpoints just to make sure in case they were higher or lower. So in this case, what are our endpoints? So let's think about the restrictions that we have on our width. So you know there needs to be a width, so it has to be greater than 0. But what's the maximum width that we can have? So imagine we had no length, and you basically just have your perimeter is going to be 2 boards that are going to be your width. So the maximum value that we can have in that situation would be 300. So they could be 300 each. So those are our two scenarios. So your width could be 0, so it could be all length, and then, or it has to be greater than 0, so it has to be anything greater than that, or less than 300, where it's all width. So let's check those endpoints. In the case of 0, you're just going to get 0 times 300, which is going to be 0. And in the case of 300, you're going to get the same thing, 300 times 0, and that's also 0. So obviously our maximum amount is going to be 45,000, and so that's the amount that we got when we set the derivative equal to 0. And so you know that the maximum dimensions the dimensions that will maximize the area are going to be when your length is equal to 300 meters and your width is 150 meters. And just as a side note, it really didn't matter which variable I chose to substitute, you'll still get the same result. And just another side note, you've seen this problem before in grade 10 or 11 math where you were studying quadratics. So the way that you solved it in grade 10 and 11 was that you set up a quadratic equation and then you completed the square to find the vertex, and that was your maximum or minimum value. So as you could see, this is much easier to just find the derivative because you know that the derivative will be equal to 0 at that point. Example number 2. A piece of sheet metal 60 centimeters by 30 centimeters is to be used to make a rectangular box with an open top. Determine the dimensions that will give a box with the largest volume. So first thing, we want to draw a diagram. Now we can see that our length is going to be 60 minus 2x. Our width is going to be 30 minus 2x. Our height is obviously going to be x. Now before we start, let's think about what our restrictions are going to be. So let's think about x. You know that you need a value for x, otherwise you don't have volume. So it has to be greater than 0, but what's the maximum value for x? So if we look at this section here, right? So if we split it in half, that would be the maximum value of x. So there would be no width, but it would just be your height doubled. So you're just kind of folding it in half. So you know that it would be less than 15. So between 0 and 15. Okay, so now let's talk about we want to maximize the volume. So let's use our formula for volume, which is really length times width times height, and let's sub in our values. So we know length is going to be 60 minus 2x. Our width is 30 minus 2x, and then our height is just x. So this is going to be v of x, because now it's in terms of x. And so I'm going to expand that. Actually, I'll just do it in one step. You're just going to have to trust me that this is correct. So x minus, actually I'll order it too. So I foiled it and I'm ordering it now. So it's going to be 4x cubed, and I've collected like terms. 180 x squared plus 1800 x. Okay, so now the question asks to maximize the volume. So maximize, we think of taking the derivative and setting it to 0. So let's do that. So let's take the derivative, and then we'll get 12x squared minus 360x plus 1,800. And let's set it to 0. I'm going to set it to 0 and also just factor out a 12 just to make it a little bit neater. So that 12's gone. And now trying to factor this, it doesn't seem factorable, so we're going to need to use the quadratic formula. So it's going to be 30 plus or minus negative 30 squared minus 4 times 1 times 150 divided by 2 times 1. And x is going to come out to two answers, so 23.66 and 6.34. Okay, so now just looking back, we want to compare these values and just making sure that they fit into our interval, so into our range. So if you notice that 23.66 is not between 0 and 15, so we're going to reject this answer, and we're going to keep 6.34 because that fits. So now we want to test the volume, figure out the value at 6.34, which comes out to 5,196.15. So that's pretty high. That seems like it's maximized, but just to check, we're going to do v of 0, and which is 0, and v of 15, which is also 0. And so it's our x value is going to be 6.34, that's our height, and then our length, just sub it back in. So 60 minus 2x, it will give us 47.32 meters or centimeters, and our width will be 30 minus 2x, and that gives us 17.32. Okay, for this example, we want to determine the area of the largest rectangle that can be inscribed inside a semicircle with a radius of 10 units. We want to place the length of the rectangle along the diameter. So if you look at this diagram, we're going to call these values, they're equal. These are your x values, this is going to be your y values, and your radius is going to come from the center to there. So obviously this point right here, we think of this as a Cartesian plane, is going to be x, y, and this value is r, and we know that r is equal to 10 units. Okay, so now the obvious relationship that we can see is the Pythagorean theorem, right? Because we know that r squared is equal to x squared plus y squared. We also have a value for r, so we know that 100 is equal to x squared plus y squared. Okay, let's leave that for a second. We'll come back to it, and let's look at what we're trying to do, which is maximize the area of the rectangle. So what is the area of the rectangle? Well, it's going to be 2x, right, times y, because your length is really 2x right here, and y is your height or width. Okay, so now we need to, let's have it all in terms of x. It's just easier that way, so we can have an equation for a of x. So I'm going to take your Pythagorean, 1 and rearrange for y. So we're going to get y is equal to the square root of 100 minus x squared, and sub that in, and we get a of x is equal to 2x, leave the x, now sub in for y. Okay, so we can rewrite that, because obviously we're going to want to take the derivative. We can rewrite this as 100 minus x squared to the power of half. So now we want to use the product rule, because we have two functions here. So to take the derivative, you're going to get 2 times, this is like your g of x, plus 2x times half 100 minus x squared to the negative half times negative 2x. Oh, and by the way, before we forget, your interval here is, because it's given in the question, you know it has to be between 0 and 10. Okay, so now let's set it to 0. Let's set our derivative to 0, and I'm just going to rewrite this. So it's 100 minus x squared minus 2x squared over 100 minus x squared. Okay, so just to get rid of our denominator, I want to find a common one, and so I'm going to multiply our first term by our denominator, and that's going to give us 2 times 100 minus x squared, right? So that multiplied by itself is going to give the at that actual value, minus 2x squared all over, so now we have a denominator of root 100 minus x squared, and so this is going to cancel out, and so we're left with 0 is equal to 200 minus 2x squared minus 2x squared, which is negative 4x squared, and so we just have minus 4x squared, and so I'm just going to skip a few steps here. We can say that x squared is equal to 50, and so x is equal to plus or minus 50. Plus or minus root 50. Now let's think about this. Can x equal negative root 50? Probably not, because we're looking for length, and you can't really have a negative length. So that is gone, and we just have positive root 50 as our answer. Now positive root 50 can be rewritten as 5 root 2, right? Because 25 times 2 is 50, so we're going to pull out the root 25, which is 5, and then we're left with 5 root 2. So that is our final x answer, so we need to plug that in to figure out what our area is going to be. So our equation for area is a of x is equal to 2x times root 100 minus x squared. So now let's plug in our value we just got, so 5 root 2, and that becomes 2 times 5 root 2. (100 minus, and this is going to be 5 root 2 squared, And then I'll just go through this step by step. So then we get 10 root 2. Here we get 100 minus 25 times 2. And so this will be 100 minus 50, which is just root 50. And when we multiply 2 times 50, we get 100, and then that just becomes 10 times 10, which is 100 units squared. And this is your max area. Now, just for the sake of time, I'm going to skip checking my endpoints, but normally you would do that as well. Okay, so now let's do a slightly more complicated example. A cylindrical storage tank with a capacity of 1,000 meter cubed is going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. The specifications call for the base to be made of sheet steel that costs $100 per meter squared, the top to be made of sheet steel that costs $50 per meter squared, and the wall to be made of sheet steel that costs $80 per meter squared. We want to determine whether it's possible for the tank of this capacity to fit into the warehouse, and if it's possible, we want to state the restrictions on the radius. So that's the first part. Okay, so first thing, let's draw a diagram. Okay, so I'm just drawing it from a bird's eye view. So this is looking from the top down. And just adding our dimensions, we know that the diameter here is 12 meters. And then we also know that our width is 12 meters here and 15 meters here. We also know that the height of the warehouse is 11 meters. And we can also conclude that the radius of the cylindrical tank is going to be 6 meters based on the diameter that we're given. Okay, so now let's find the volume of the warehouse. So that's easy to find. We're just doing length times width times height. And we're going to get 12 meters by 15 meters by 11 meters. And that gives us 1,980 meters cubed. Okay, so now let's go ahead and find the volume of the cylinder. And so if you remember, the volume of a cylinder is pi r squared h. That formula makes sense because it's really the area of the circle times the height. And so now we can plug in values for this. So we have 6 meters squared, and we have a height of 11 meters. And so we know that the volume of the cylinder is going to be 1,244.07 meters cubed. Okay, so it looks like it fits because the volume of the cylinder is less than the volume of the warehouse, but we want the volume to be capacity, which is 1,000 meters squared or cubed, as given in the question. So let's set that to equal our volume so we can figure out our range for our radius. And so solving for r, we would get square root of 1,000 over pi h, and this comes out to 5.38 meters. So now looking at the restrictions of the radius, we know that the radius has to be anywhere from 5.38 to 6 meters. Part B asks, if the tank will fit inside the warehouse, determine the dimensions of the cylinder that will minimize construction costs. So to do this, first I want to draw a diagram, and I'm going to look at this in terms of surface area. So I'm imagining that I'm taking all my surface and I'm just kind of spreading it flat like this. So here's your top and bottom. Now if we roll that middle part of our cylinder out, we know that this is going to equal the circumference, which is just 2 pi r. So that is this length right here. And you know that obviously on your circle your radius is r. And I'm just going to write down our prices for each section. So we know the price for this piece right here, the top circle is $50 per meter squared. That was given in the question. This middle part is going to be $80 per meter squared, and the bottom is 100 per meter squared. And we also just want to label this. This is our height. So now we want to come up with an equation for our cost. So our cost is going to be equal to the price of the top times the area of the top plus the price of the middle section, I'll call it M, times the area of the middle section plus the price of the bottom times the area of the bottom. Okay, so let's sub that in. So your price of the top is 50, and the area of the top is just a circle, so pi r squared, plus the price of the middle is 80, and then the area of the middle is 2 pi r, right, because it's essentially a rectangle, times your height. And so just to show you, 2 pi r times your height. Okay, plus 100 is the price of the bottom, and that is another circle, so pi r squared. Okay, so now let's simplify this, collect like terms. We're going to get this and this collect, so it's going to be 150 pi r squared plus 160 pi rh. Okay, so this is great, except we have two variables. And so we have r and h, and we want to get it in terms of one variable. So we need to introduce another equation. And so we're going to use something we used from part A. And we knew that the volume was equal to pi r squared h, and we knew that that was 1,000 pi r squared h. And so I'm going to solve for h here and get 1,000 over pi r squared. Take this, substitute that into there, and so everything is now in terms of r. So that's really useful. So now we can solve for c of r. So c in terms of r, and just sub that in. 160 pi r, so it's going to be 1,000 over pi r squared. This r is going to cancel out with that, and the pi's will also cancel out, and so we get 150 pi r squared plus divided by r. In this situation, to avoid using the quotient rule, we can just rewrite our C of r like this. Now, since we want to optimize the cost, we need to take the derivative. And remember, when you're taking the derivative of this, that pi is really just a constant. So it's just a numerical value, so we're going to treat it as that. So it's going to be 300 pi r minus, right, because we're bringing the negative 1 down, and then we're just going to get 160,000 over r squared, or r to the negative 2. And so set this to 0. We can just rearrange the equation by bringing it to the other side. Now cross multiply, and now just solve for r. And r is going to be the cubed root of 160,000 divided by 300 pi, which is just 5.54. Now let's go back and use what we substituted for height earlier. So we said height was equal to 1,000, that was the original volume, divided by pi r squared. And so we're going to get, just subbing it in, 5.54 squared. Our height is going to be 10.38 meters. And so again, just to go over what we're actually trying to find, this is going to be the radius and the height of the dimensions, like the dimensions of the cylinder, that will reduce your construction costs. So based on the surface area costs that we calculated earlier. So now we want to check what our actual costs will be. So let's take our value that we got. So the cost at when the radius is 5.54, and you're just going to have to trust me on this one. I'm plugging it into the equation, and we get 43,344. And of course we want to check all our points. So we found our range for the radius earlier, and our value was 5.38. That was from part A. And the value for that is 43,380. And I also want to check our other endpoint, which was 6. And so that is 43,622. So just comparing these values, we can see that the value that we just got is in fact the lowest. So our endpoints, this is within our endpoints, and this is the value that we just got by maximizing or optimizing our cost equation and coming up with this and checking the endpoints. They're kind of all within the same range, but obviously this is definitely more of a min. So the min cost for this the cylindrical structure would be when the radius is at 5.54 meters and the height is at 10.38 meters. Okay, last example. A real estate office manages 50 apartments in a downtown building. When the rent is $900 per month, all the units are occupied. For every $25 increase in rent, one unit becomes vacant. On average, all units require $75 in maintenance and repairs each month. How much rent should the real estate office charge to maximize profits? Okay, I'm going to let X, in this case, be the number of units. So all you business people know that profit is equal to revenue minus cost. So now let's just take what's written here and translate it into math. So 0.9 for every $25 increase, we're losing one apartment out of the 50. Okay, that's our revenue. Now let's subtract the cost. So we know our maintenance fees are 75, and that still applies. Okay, so now that we have our profit equation, we can expand this, and we're going to get I'll collect like terms after, plus 1250x minus 25x squared plus 75. Okay, so just to collect like terms, we're going to get negative 25x squared plus 425x plus 41,250. Okay, and we want to maximize our profit, so take the derivative. We'll get negative 50x plus 425, set it to 0. And I'm just going to skip a couple of steps here. X is going to be equal to 8.5. So looking at this on a practical level, we can't have 8.5 units, so we need to either round it up or down. So we have two choices here. X can equal 8, in which case we will have 900 plus 25 times 8. So when we're trying to figure out how much rent to charge, it's going to be either $1,100, or if x is equal to 9, we would have 900 plus 25 times 9, which is $1,125. So in this case, your rent should either be $1,100 or $1,125 to maximize your profit. And if you want to verify, you can plug in both values, x equals 8 and x equals 9, into your profit equation, and you should get the same value of 43,050. So just to summarize our process here, what we want to do when we're dealing with these kind of problems is firstly identify quantities that can vary and determine the function in terms of one variable to be optimized. So we'll usually have more than one variable, but we want to say everything in terms of one variable, so you want to substitute as much as you can. And then number 2, we want to draw a diagram. This definitely helps. Step 3, determine the domain of the function to be optimized, so your interval endpoints. So you might have to use common sense in most cases, kind of think about the situation and try to figure out what your max and min values for your variable can be, and try to use the variable that your independent variable that you're using in your equation. And step 4, we want to determine max or minimums. So taking the derivative, setting it to 0, and then solving for your variable. And then we want to answer problem in terms of the given context. So you're going to check your endpoints and then give the answer that makes the most sense.